Welcome to my channel. Some time ago, Scott Manley uploaded a video where he was talking about artificial gravity made by rotation. Maybe you know him, it's as usual an entertaining and well-researched video. I think most people that are interested in space stuff are thinking about this every now and then, and so do I. I just wanted to get an idea of how this would be like, and also I just wanted to visualize the actual rotation, so I did some calculator science on this. Let me start with a quite small rotating space station with a radius of 5 meters, roughly 16 feet. And I need some example numbers, so the guy will be 80 kilogram of mass. Of course I want 1g of artificial gravity, because why not? And 1g will cause an artificial weight force of 784 Newton or 176 pound force. You might notice that the radial force of 1g will only be generated at the outmost radius of the station, and it will be 0 in the center. That means if the guy is 1.8 meters tall, that's 5'11", his head will rotate at a radius of just 3.2 meters, and at this radius he will only get 0.65 g. I will not go into details what this would be like and neglect this force gradient and the Coriolis effect for the sake of simplification. Also, these effects are reduced as the diameters get bigger. Of course, if I talk about rotation, I have to specify which parameter I'm talking about. Rotation can be expressed as an actual velocity around a given circumference, that'll be meters per second, which goes down to 0 in the center. Or it can be the angular velocity, which does not change at different radii and has degrees per second or radians per second as unit. Or maybe we take the good old RPM, which counts 360-degree turns per minute. First, I looked at the circumferential speed of the outmost wall of the station that would provide 1g of gravitational force. There's a little formula, it goes like this: force times radius divided by mass and the square root of it all. That is 784 times 5 divided by 80 and square root. I get 7 meters per second, about 23 feet per second, and one revolution would take about 4.5 seconds. That means the guy would have to move at 7 meters per second in a 5 meter radius to have 1g of artificial gravity. And that's what this would look like. 1g, 7 meters per second in a 10 meter space station. Yes, it's amazing. Here's an interesting side note. If the guy started running against the rotation with exactly 7 meters per second, which is possible for a reasonably trained astronaut, he'd cancel out the rotation and get 0g and probably starting to float around. And the other way around, if he would run with 7 meters per second in the direction of the rotation, the velocities would add to 14 meters per second. So it's 2g? Nope, it would be 4g, because the speed is squared in the formula. He'd probably have a hard time to run in the rotational direction. This will happen in every rotating environment to some extent, but all of these effects will be reduced as the diameters grow. So let's go on. In a 20 meter space station we need 9.9 meters for 1g on the outer wall, and you see 40 meters it's 14 meters per second, 80 meters it's 19.8 meters per second, 160 meters it's 28, 320 meters it's roughly 40, all up to 88.8 meters per second at 1609 meters, which is 1 mile. I chose a mile as biggest diameter because that happened to be the diameter of the fictional space station Babylon 5, and yes, I have watched this show. You see the circumferential speed increases significantly, so does this mean the bigger the space station gets, the faster it needs to rotate? Only in regards of circumferential speed, not in regards of angular speed. The angular speed goes down, here's the visualization, because the circumferential velocity to reach 1g is a product of velocity squared. The increase needed to maintain 1g is flatter than the increase in circumference, which is a plane product of pi and diameter. So the meters per second go up while the RPM go down. That's just the laws of physics applied. Okay, that's it, my little addendum for Mr. Manley's video. Thank you for watching. I plan to upload more of this side note kind of videos, so like and subscribe for more. Thank you.